Welcome to Q&A week 2. So at this point, you have taken quiz 1 and quiz 2. And you're learning that the multiple choice questions are very challenging. And you're doing pretty good with the open response. Now, Thursday, which is tomorrow, you will have exam 1. Now, exam 1 is going to be very important. You're going to want to do extra well on those multiple choice questions, folks, because they're worth 6 points apiece. So when you log on there, you're going to see that you have 25 multiple choice questions, and it's going to say 75 points. But because exam 1 is worth 200 points, this is going to be times 2. Okay, so that makes each multiple choice question 6 points. It's either 6 points that you get right or 0 points, okay? So this will total up, and that'll be 150 points. So you have to know that each one of those multiple choice questions are written to test a certain concept, okay? So a lot of times there are 2 close answers, so don't be hasty. You do have 2 hours. So Sapling will give you 2 hours once you log on. I do have it set for 24 hours. Now, I want to take the stress off. I do expect you to turn in your exam, your open response, and your Sapling, the goal, by 5 p.m. Okay, that gives you 8 hours. I open everything up at 8 a.m. and I expect everything in by 5 p.m. Now, some people have emailed me, they have conflicts in schedule. Okay, well, if you have a conflict in schedule because you have to work or something, you can either do it in the morning or you can do it until maybe midnight. Okay, because if you turn it in before midnight, it's still the same day of the assessment. Now, you'll notice that I've extended it to 5 p.m. the next day. I have been asked, would I give late points and charge late points? At this point, I don't want to do that. I want you to know what you're truly getting assessed for and what your assessment points are. The reason why I have extended that is because the answers are released, okay, upon that deadline. Some people have serious issues. They might be an IT issue. They might have a family member that might be at the hospital. So there are those exceptions. And I want that student to be able to log on and be able to get their exam or their quizzes due at noon the next day. Okay? So those are those 1 or 2 people that have those issues. I don't want the same people always missing the same deadlines, okay? So at some point, I know we just started that first week, and this has been a lot, but we're on week 2, okay? So at some point, you have to work twice as hard to get ahead of the curve. So I'm expecting that if that is you, that you're going to get there, because I want you to be leading and not following in your own schedule, your own management of time, okay? Because if you can get ahead of that calendar, you're going to do better. I think you're going to do a whole letter grade better. So if you are probably functioning as C, I think if you can get ahead of that calendar and those due dates, you're going to be functioning at a B. Okay? So that is the deal with the assessments and the deadlines. Okay? I know that organic chemistry is a new language and it's a science and it's challenging, so I'm trying not to make everything stressful. I think summer classes are somewhat stressful because every assignment that I have given you and every expectation of what you're doing, I usually have over a 16-week course. Okay, that means students have a lot more time. You're doing this in a 6-week course. Okay, so if it feels like a lot, well, folks, it is a lot. Okay, but this is the expectation. You have to do those learning exercises in order to master the material. Now, another question I was given was, how do I suggest you do better on quizzes? We know that the quiz grades are lower. 55% are the average quiz grades here for multiple choice versus 80% on the open responses. Okay, your open response on exam 1 is going to be 50 points, and your multiple choice are going to be 175 points. So how do we get this 55% up? Well, hopefully you're figuring out how to use Sapling, right? So you're not having any IT issues, and that's your homework grade. I think everybody's going to be fine with the homework grades as long as you're doing the assignments and you're getting the immediate feedback. Now, Poggle is going to help you with your open responses, okay? But I'll tell you what's going to help you with your open responses and your quiz grades, and most importantly, your quiz grades are the book problems, okay? So I have given you problems out of Wade that are at the back of your chapter, and then I've posted a YouTube video link that talks about how to work each one of them. Some of these videos are hours long. Why are they hours long? Because that's how long it takes to solve the end of the chapter problems. I have gone through there and I said, this is a good problem, work this one. This is a great problem, work this one. And if you actually go and you work the problems on your own on a single piece of paper, then you can check your answers on the video. If, however, you look at the video and you think that you're just going to lay there and listen to the video to help you solve the problems, it will not help you. Okay? So you need to struggle with working through the problems and the book problems, and then you need to check your work on the video. This is your best way of improving on your assessments. Okay? Guarantee it. And people have taken my classes before, and the students that get A's typically are working these book problems every day. Okay, but I would say work the book problems after you've done Sapling and Poggle, simply because you're getting points for these. Okay, so and that should help you. Okay, so I'm looking at some of my questions that people have emailed me. So we've talked about the time on the assessments and the expectation, how to improve that quiz grade, okay, and your exam grade. Keep in mind, if you find this extremely challenging, think about this. You're at your home and you have your resources, you have your notes. Okay, I know it's still challenging, but when I usually give these assessments, students don't have a piece of paper. They have to memorize all of their PKA values. Okay, so that's the expectation. I know that you have access to your notes, and I'm not going to fight it. Okay, so that's fine. And I don't necessarily think that's anything's wrong with that, because I have access to the answer keys in the notes as well. Okay, so now we're going to get into some questions regarding the material. So some of the questions we've had regarding the material include bullying points. So we're going to work some bullying points. I've got some bullying point questions. We have some acidic proton questions. And so these I will work by going over your quiz 2. And then we also have the Poggle. The first week we had the resonance structures. So I'm going to go over that, and that's going to be, I think, problem number 11. I will work the whole completion. I'm turning to that page right now, folks. And that is problem number 11, page 21. And I think if we go over all of these, that should help you. Your second week Poggle, I'm telling you, I haven't seen any issues. I'm very impressed with second week Poggle. So, excuse me, I think that that is encouraging. So I don't have anything to say other than watch those lecture videos and do those Poggle exercises before you take your assessment, okay? Because I need you to do well on your assessment grades. Okay, so first of all, let's go over the quiz 2, and we'll talk about these different problems. So quiz 2, problem number 1, you were giving this structure. All right. Now, another thing I want to say is I've been looking at people's structures, and there's a portion of the students that are not put in proper formal charges. This is not acceptable because the first Pogel exercise is writing Lewis structures. Correct Lewis structures include lone pairs and formal charges. Okay, if you have to go back and you have to rework Pogel 1 over and over and over in Chapter 1, I'm going to tell you do it because you're going to lose points every assessment all the way through Organic 2. The number one thing you have to do when you're solving these problems is to draw correct Lewis structures. Okay, so what I do, the first thing I do is I put in my lone pairs because if we're going to draw resonance structures, we've got to know where the lone pairs are. Okay, so if oxygen has a negative charge, it has 3 lone pairs. If it's neutral, it has 2 lone pairs. Nitrogen with a positive charge has no lone pairs. Some people want to put lone pairs on this carbon here. Okay, that carbon has a plus charge. That means it, if you want to, you can draw the hydrogen in there. Okay, that means carbon has 3 bonds. And then we have these 2 electrons here that's in this bond here. Okay, some people are having trouble hybridization. This first carbon here is an sp2. How do you know? Well, let's look. It's connected to 1, 2, 3 things. So if you add up the superscripts here, S1, P2, what's 1 plus 2? 3. 3 things. I call them things so we don't focus on the double bond. Okay, what about this one here? Let's go to the next one, this carbon here. 1, 2, 3. That one's sp2. Okay, let's go to the nitrogen. Nitrogen is in resonance, and it has 3 things. 1, 2, 3. That's sp2. Okay, these oxygens are sp2. So that means the ones that are in green here all can participate in resonance. Who cannot? Cannot participate in resonance. That means do not push electrons there. This carbon is an sp3. If you need to, you can draw the hydrogens in. Okay? It's connected to 4 things. 1, 2, 3, 4. That makes it sp3. This carbon cannot either. It's an sp3. So only these green that I've highlighted in green can participate. That means we push electrons. Now, a lot of people are drawing lots of electron flow arrows. Okay, I would recommend not drawing lots. I would recommend if you're pushing negatives, and you start with the negatives, you start with the negative charge because that's in electrons, you're pushing electrons. Draw 2, okay? Draw 2 arrows. If you are dealing with a carbocation, okay, so electrons, you're going to draw them from the electrons, the negative, towards a delta positive center. If you're dealing with a carbocation, you're going to find either a lone pair or a pi bond, and you're going to draw it towards the positive, okay? You're going to draw it towards the cation, and you need to draw 1. The reason why I say only draw 2 electron flow arrows or 1 is because you're going to pick up more resonance structures. I have been very kind to you all in the assessment. I have only asked for 1, okay? I have taken assessments and I've seen assessments given where they ask for all of them, okay? I just want to see, do you know how to draw those electron flow arrows correctly? Do you know how to redraw the structures and formal charges? Okay, and I don't feel like torturing you with 4 of them that are incorrect. Can you draw 1? I might ask you to draw 2 on your open response on your exam. Okay, so we start with this negative charge, okay? And I'm just going to draw 2. So I'm going to push this towards the nitrogen, and the nitrogen already has 8 electrons. We cannot break octet, so then we got to push the pi bond to the lone pair here. So we're going from a lone pair to a pi bond, and we're going from a pi bond to a lone pair. And then I wanted to see the resonance arrows, folks. That's the double-headed arrow, not equilibrium arrows. So that was worth a half a point on your quiz. Wait, I'm going to redraw all of this other stuff here, okay? I'm going to draw all the carbons and everything. The only ones that participated were those red electron flow arrows. So these 2 electrons stayed. These went to nitrogen. Okay. And then these electrons here went here. Now oxygen has 3 lone pairs. It gets the negative charge. And these 2 electrons went to a pi bond. Oxygen's neutral. And now nitrogen has 4 bonds. It needs a positive charge. Okay, so then I want to check my overall charge. I have a plus, and a negative. So that makes its overall is a +1. I'm going to check my charge. Okay, I have a plus and a negative. So overall positive. Now let's draw another one. Notice I only did 2 electron flow arrows there. So we're going to do another one here. Okay, so this one I also have, you see how that's an sp3? I can push these electrons there. Okay, so I'm going to go from a pi bond to another pi bond. And I'm doing a cation. See, I'm pushing those electrons towards the positive carbon. And then I'm going to redraw. I only need 1 electron flow arrow when I'm dealing with carbocations. I'm going to draw these the same. I did not bother the nitrogen and the oxygen because I don't have my electron flow arrows. Now what I did change was I changed this 2 electrons to go here, and that puts the carbocation now on that nitrogen. I'm going to check my overall charge. I've got 2 positives and 1 negative, so overall positive. And that's all you can do. Those are your 2 electron flow arrows. 3 resonance structures. 3 resonance structures. That's all you can do. So that's how you know how many, because you see your sp2 carbons. All right, let's do number 2. Okay, so number 2, question number 2. I want to see you draw this Lewis structure. Folks, you have your functional groups, okay? If it's not a functional group you can name, odds are, I mean, I'm just telling you, it's not a valid Lewis structure. Okay, you have access to your books. You can look at most of the time I already have students, they have to have memorized their structures. Do you see how this is NCCHO? Well, you start with nitrogen, connected to a carbon, connected to a carbon. CHO, you need to recognize that that's a double bonded oxygen with a hydrogen. Okay, now, and then your lone pairs for nitrogen. Carbon, how many bonds does carbon like? Let's go. Hydrogen. Hydrogen has 1 bond. Oxygen, 2 bonds, lone pair. Carbon, 2. And then this carbon there's no hydrogens coming off of this carbon. So that tells you right there, this needs 4 bonds. So there's your 4 bonds on a lone pair. Now you can add up. You can do your thing where you add up the total valence electrons. Okay, nitrogen is group 5. Carbon is group 6. Hydrogen's group 1, and wait a minute, I think carbon's number 4, isn't it? So let's change that. Okay, so we're adding group numbers for total valence electrons. Carbon is 4, there's 2 of them, there's 1 hydrogen, and there's an oxygen. So that's 10. Do we get 20? Should I get 20 valence electrons? Okay. And then you count your electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20. There's no charge here. Okay, so it has to be neutral. This is neutral. And then is every atom must have its complete octet. And remember, for hydrogen, it's 2 electrons. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So yes, this is valid. And then you need to do your hybridization. So what's the hybridization of nitrogen? How many things are there? 1 thing, 2 things, 2 things. So it's sp, okay? If you added up the superscripts, you would see 1 plus 1 is 2, sp. Carbon, This first carbon, two things, sp. This carbon here, how many things? 1, 2, 3. That's sp2. Add the superscript. 1 plus 2 is 3. That's sp2. We don't do hybridization for hydrogen. Oxygen, it participates in resonance, and it has 2 lone pairs. We have 1 here, 2, 3. So that is sp2. We know that sp is linear. That means between the things you have 180 degrees separation. sp2 is trigonal planar. I also call that just flat, okay? And that means between each thing you have 120 degrees. sp3 is tetrahedral, and we're learning that you usually have a dash and a wedge, something that comes at you, something that goes away, and then the line is in the plane, okay? And so these things are 109.5 degrees separation, and that's the geometry. Shape matters because we're going to be getting into reactions, and the shape determines the reactivity. All right, so we're going on to question number 3. Okay, question number 3, we're dealing with physical properties. So, and one of those are boiling points and melting points. So one of the biggest things is to define your intermolecular forces. Okay, so we talked, I had a lecture video on that. And these you need to recognize your functional groups. A lot of people did pretty well on this problem. So when you have this compound here, you say, okay, this is an alcohol. Okay, you'll find that that's an aromatic alcohol called a phenol. But alcohols have lone pairs, oxygen, with a hydrogen bonded directly to it, so it's a hydrogen bonder. Okay, that does hydrogen bonding. Compound, so that's A. Compound B, okay, sure, it has dipole-dipole, but higher than that, the dominant force is hydrogen bonding. Okay, hydrogen bonding is the reason why water does 2 hydrogen bonding. And what's the boiling point of water? 100 degrees Celsius. I mean, folks, this is 18 molecular weight. I mean, you compare this to CH4, that's 12, 13, 14, 15, 16. 16 molecular weight. What is methane? Methane is a gas. Okay, so this is how dominant hydrogen bonding is in these boiling points. Now, carboxylic acids can form a dimer. Okay, so let's see if I can draw this upside down here. Okay, so what happens is it can do a dimer. So these hydrogen bonding here makes it the highest boiling point out of this group. Okay, so that's a carboxylic acid. The only thing I have to check, like if you have a carboxylic acid, amides typically have can have higher boiling points than carboxylic acids, but those are your highest functional groups. And so this is hydrogen bonding as well. Okay, and that's going to be more dominant, more impactful than dispersion and dipole-dipole. Keep in mind, if they have hydrogen bonding, they also have dipole-dipole, and they have dispersion. So, and this is toluene, and this just has carbon and hydrogen, so that's going to be dispersion. Okay, you pretty much have to have a heteroatom to have any dipole-dipole, and this is always going to be your lowest boiling point. Boiling point and melting points kind of mimic each other, so if you have Typically, if you have a higher boiling point, you also have a higher melting point. So you just kind of have to understand your trends. Now, one of the questions I had was about what if you have a bunch of alkanes, okay? And how does that affect so if they all are dispersion, okay? So the number one thing is you actually would calculate their molecular weight. So if you have hexanes versus butane, okay, so hexane has 6 carbons, 1, 2, 3, 4, 5, 6. Butane has 4, 1, 2, 3, 4. Hexane is going to have a higher melting point and boiling point than butane. And then if you get into branched, okay, so, and I have this in my book on chapter 3, we're looking at page 153 and 154. Branching, so something branches, so this is versus pentane, 1, 2, 3, 4, 5. This is pentane. And this is 1, 2, 3, 4, 5. So these have the same molecular formula, molecular weight. This is going to be a lower boiling point than pentane. So this is called the straight chain. Sometimes you'll see N pentane for straight chain, and this is branch. This is called a branch. And the branch will have a lower boiling point. Now why is that? Because it has a lower surface area. So I think about if you put butter in a pan and you want to increase the rate at which it melts, what do? You have smaller surface area because you chop it up, okay? So that's kind of what's happening here. It minimizes the stacking, so you lose the stacking of the van der Waals. Because when you're talking about boiling points and melting points, these physical properties, they're determined based on their intermolecular forces. And so branching will break up that intermolecular force. And when you minimize that, when you can break that up, then you can decrease the temperature at which these properties, boiling points and melting points, happen. Okay, so I'm looking at my list of questions. We are going on to, let's do 4 and 5, and then I have some questions about 5 and 6. Okay. Okay, so question number 4, quiz number 4 question. Yes, you're going to have to be able to do this. This is important. And when I think about the POGIL, I've made some corrections. So on the reactant side, you're always going to have to define, so the first thing you're going to do, you want to define an acid and a base. Now folks, sodium hydroxide will always be a base. It's one of those strong bases. Whenever I see sodium, any group 1, group 2, I make that a positive, and I would go ahead and make that a negative. Because when you go ahead and you sign full negatives, now that's where you're going to start with your electron flow arrows. Reactions happen based on flow of electrons. We're not in nuclear chemistry. Okay, nuclear chemistry is about the nucleus and generates energy, and you're changing one element to another element. It's the total way to try to make gold, right? But we're doing the other chemistry, which is making and breaking bonds. So in an acid-base reaction, we're going to abstract a proton. Okay, we're going to extract a proton. So we've got to figure out where is our acidic proton. And here it is. And that makes this an acid. Okay, so you can go ahead and put in your electrons there. I like to put in my lone pairs. Remember, we start these with correct Lewis structures. And just because you're given them, I could have given this to you as CH3, 2CH, CH2OH. Folks, I would never try to solve a problem like that. I would totally make my line drawing with my lone pairs, and I would draw it out, okay? Because I can give you a problem like that, but this is what you need. You need to start your problem solving with correct lone pairs. Now, the electron flow arrows, you're going to have, once you define that, you need to draw in your electron flow arrows. Not everybody did that. I didn't think I put it on there, but you will see this in your response. So this is your base electrons going towards your acid proton, okay? And you're also going to have to draw two. So you're going to need two electron flow arrows. One, the base going to the acid, and then those electrons have to be given, in this case, to the oxygen to make a conjugate base. And then your base is going to take the acidic proton to make a conjugate acid. Okay, so you need to show this. So those electrons are going from the base to the proton, and those electrons are going to be given to oxygen. So there's my two. And then we draw the conjugate acid and the conjugate base. You need to label these and draw these. So here, the conjugate base is the oxygen that lost the electron. You got sodium's just floating around, okay? It's just in solution. Sodium's a full positive. It will hang out over here with the negative. Don't put them next to this one over here, okay? And then this one, what is that molecule? You know what that molecule is. Now that you didn't put it with sodium, that's water, okay? You know water. Water has a pKa value of 15.7. You all can look at charts like that. My students normally have to memorize this. This is an alcohol. I don't expect even the exact one. Some people want to put the exact one. Keep in mind, I make my students memorize alcohols have a pKa range from 16 to 18. All right? 16 to 18. This one would probably be 17. Butyl alcohol, more the branch, has a pKa of 18. Just methanol or ethanol would have a pKa more 16. I don't expect you to differentiate between the two. Okay, 15 to 16, and this one's about 16. That's going to be an equilibrium, 50% over here, 50% over there. Usually if these numbers are between 10 to 100, you could say they're pretty much the same equilibrium. Okay, so 16 and 16 is 0. If this is 16, that's 18. 18 minus 16, that's 100 times different. Okay, now did we do everything? Yes, we labeled our pK values, so you need to draw the conjugate acid and conjugate base, and then you need to assign pKa values. Now folks, you only assign pKa values to an acid and a conjugate acid. We can only compare two numbers. Okay, we only compare two numbers. And then the fifth thing you want to do, draw in your equilibrium arrows. That's the last thing you do. And it will always, say this 5 times a day until you know it, always the equilibrium arrows will point to the higher pK value. Okay, so if this is your higher, so if you have 20 and a 5, which way is it going to go? Towards the 20. If it is 20 and a 5 on the reactant side, it's going to go that way. If it's somewhere between like a 16 and a 17, you can just draw those equal. If you do draw them in not equal, they better be pointing more towards the higher number. Your higher pKa value is your weakest or the weaker acid. And that's how you do acid-base reactions. That's your first reaction in organic chemistry. Like I said, you're going to probably have about 180 by the time August gets here. I'm the messenger, folks. So if that seems like a lot, I did not write the curriculum. I am the teacher. Okay, I'm here to help you. All right, now we're going to do 5, and we're going to talk about acidic protons and resonance structures for 5 and 6. Let's see. So question number 5. You're supposed to pick between these two structures, and you're supposed to predict which one's more acidic. Okay, so when you're predicting which one's more acidic, you need to draw the conjugate base. So a lot of people did this, and so that means like a base comes in and takes this proton, okay, and then what's that structure look like? There's your acidic proton. So you can draw the conjugate base here, and this one here looks like this. All right, so here's your conjugate base here, and then your conjugate base here is this. Now, let's look at this compound here. You see that carbon? That carbon is sp3. What's not drawn in there is hydrogen. Okay, it doesn't have a plus charge. So that's still an sp3 carbon. It doesn't, it still has this hydrogen. Okay, what do we know about sp3 hydrogens? We can't draw, I can't put electrons there. I can't put these electrons there. I can't put these electrons there. Okay, so we would say this is one resonance structure. Now, resonance structures, so what's the difference between carboxylic acid and an alcohol? Okay, this has a resonance structure. See my resonance arrow? All right, so that's, and we would say this has two resonance structures. We said this has one resonance structure because we count itself. Okay, what's the pKa? Let's say the pKa of this is 5. What's the pKa of an alcohol? 16. 16 minus 5 is what? 11. That's 11 zeros. 9, 10, 11. Okay. That's how many times. That's what a resonance structure is worth for making something acidic. Okay. So here we have this. This alcohol has a pKa probably around 16. Now, what about these resonance structures? Do you see? This is an sp2, 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 sp2. Okay, so what does that mean? That means these electrons can go there. These electrons then will turn into, so we're going to go lone pair goes to a pi bond, and pi bond goes to a lone pair. And notice I'm dealing with a negative charge. I'm pushing those electrons into that ring, and I'm only doing 2 electron flow arrows. Everything else stays the same except here. Those electrons went here, and then those electrons became a negative. All right, and then we do it again. That's going to go a lone pair to a pi bond, and then we're going to have the pi bond go to a lone pair. And then I'm going to redraw this resonance structure. In graduate chemistry courses, I literally would have to draw resonance structures and count them, because these were molecules you can't just look up and find to figure out which one's more acidic. And you can literally just count the number of resonance structures. All right, and then if you do this again, you'll see that that goes right back to the original structure. So how many is that? 4 resonance structures. This pKa is 10. So 10, so there's 6 zeros times more acidic. Okay, so the last problem we're going to work on this Q&A is problem number 6. Okay, and then I did get an email question regarding this problem here. And I'm going to try to answer it the best I can. It was a good question and something I have struggled with explaining to my students time and time again. Okay, so some people wanted to say HA. Okay, this is not an acidic proton. You'll recognize that as a aldehyde. Okay, aldehydes, the HA, if you take it away, makes it a carbon negative. So what does that look like? So if you took a base and you took the HA away, those electrons would have to go in carbon, and you wanted to draw that conjugate base. So let's look at that. Okay, so what is that structure? Well, So if you wanted to say, okay, let's put those electrons here, all right, what does that look like? And this is my best way of explaining this, why this does not happen. So 1, 2, let's count them. 1, 2, 3, 4. Okay, how many electrons? What's the number of electrons on oxygen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Octet violation. If you look up acidic protons for an aldehyde, if you Google it, they're going to talk about something called alpha hydrogens and alpha carbons. And we're going to talk about this. This is chapter 22, and it's all about enolates. But folks, that is something like this. Okay, that's not this proton. It's the alpha carbon hydrogen. Okay, so this pKa is around 20. And so if you have a base, to take that one, and you drew the conjugate base for that, now you have a resonance structure here, okay? And that's why that is an sp3 carbon that has a pKa of about 20, not 50, okay? So it does drop it by about 1 and 30 zeros acidity because of resonance, okay? But that's called an alpha carbon or an alpha hydrogen. That is not this HA here, okay? So that is not happening. HB is on an sp2 carbon. I think the pKa of those are around 35 or 40, all right? Not going to happen. Okay, what about this one? If you have an HC, and a proton on a heteroatom such as oxygen, okay, so that hydrogen is connected to an oxygen, a heteroatom. Now we're talking, because that oxygen can support that negative charge. So when you draw its conjugate acid, conjugate base, then that negative charge can be supported by electronegative oxygen, and you can also draw resonance structures, and so that pKa is about 10. Okay, so I hope I was able to explain your questions. Very good questions. We are in week 2. It is coming together. I just got another question in. Okay, so I've wrote down everybody's question, and this happens to do with drawing chairs in POGIL week 2. So I'm going to add another page and go over this question, and I'll read it out loud. Okay, the question is, does the up and down direction of the bulky group matter? Is it simply the equatorial position? It is the equatorial position. It's the equatorial position that matters. Okay, up or down is relative. Okay, right or left, when you're naming these, is relative. So even though I might draw, let's say, something like this, okay, so even if I draw that, I can draw this is, okay, so we say that's coming at us. I can still draw it like that. Okay, so that is equatorial down. But what does matter is I've got to get this carbon number 4. So 1, 2, 3, 4. I got to get carbon 1, 2, 3, 4. It better be on the same side. That's what I'm seeing. Okay, so this is cis. So this is cis 1 isopropyl dash 4 methyl cyclohexane. I've got to make sure this is cis. So the best way to do that then is, let's see, this is up, down, up, so down, down, this is down, this is my CH3 here, okay? And then these have to be on the same side. And so yes, this is cis. Equatorial, the reason why this is going to be equatorial is you got to understand these single bonds, these are rotating. And when they're rotating, they need a lot of space. Okay, they're like those big fans on those turbine. Okay, and if it was in this position here, okay, it's going to, when it's rotating, it's going to hit the, the hydrogen over here, and this is called a 1,3 diaxial interaction, okay, interaction, and this is bad, all right? So if this thing is rotating here, you don't want to hit here, and that's why your bulky groups need to be equatorial. Tert-butyl, this is isopropyl. A tert-butyl, they even call this a locking group, okay? So it's only going to try to be equatorial. For example, if I were to have a tert-butyl group and a methyl group as a substituent, would be okay that the most stable has the tert-butyl equatorial down and the methyl axial up. Yes, okay, up and down doesn't matter. You have to put, it doesn't matter whether that tert-butyl is up or down, it's the relative position. So if these are both on the same side, like I said, this is just as correct, okay, as long as they're both cis. Okay, well, I hope I answered your question. It was a good question. I'm going to post this Q&A. And also, one other thing I wanted to say. My daughter is a pole vaulter. I think I told you all that. And so I have to get her to pole vault practice, whatever she's going to do tomorrow. So I usually lose a half a day somewhere. So I might be unavailable from my computer for about 6 hours tomorrow, and that happens to be our exam day. So you're welcome to text me. Okay, I have my phone. I'll put my phone number here again, 859-684-1703. If you have something that's important that it can't be until like 6 o'clock or 7 o'clock at night for me to answer. So if I'm not responding to an email, you can always send an email tomorrow. You could text me or you could call me. You get my voice. You all hear my voice. Tell me who you are. I'll answer the phone or I'll respond to text. Even in text, tell me who you are. And if I can help you solve your issue, I will. My goal is to get these assessments and get the feedback and get your grades without the stress. So I know if you're stressed out and you're taking an exam and you have something happens, waiting 6 hours to communicate with me can feel like an eternity. Okay, so I don't want you to feel that way. So if you need to in a situation like that, you're welcome to text me or call me, and I will do my best to help solve your problem. All right, well, good luck and keep the emails rolling. Okay, bye-bye.